This diagram in front of us here is a very simple representation of how an electric motor works. If you watch that video that I posted first there about where the energy comes from between the interaction of the electric field and the magnetic field, um, which, like I said, blew my mind, uh, we're going to apply that here in this diagram to create a magnetic field in that bar there in the middle by running a current of electricity through those coils of wire. The number of coils and the length of the wire is going to determine the strength of that electric field as well as how much current is flowing through it. That electric field strength will line up the magnetic domains in that bar there. The atoms or the molecules of that material are actually polar. They have a north side and a south side. And in a non-permanent magnetic material, those things are all jumbled together and pointing in all different directions. And it takes that electric field to line them all up nicely so that they can create a nice strong magnetic field. That strong magnetic field then interacts with the permanent magnets that are on either side of the system and creates a torque, creates a moment to spin that armature around, because obviously we've probably stuck a dowel in the middle of that north-south center pole there, right here, that would cause this to rotate. Now, in an electric motor, we have to have some system that will change this north pole as it moves this way and gets attracted to this south pole. It has to turn this side into a south pole so that it can continue that rotation. And it has to change that thing as soon as it gets to this position where it's most attracted to that south side so that it can continue on. So this is a little bit more complex diagram of a DC motor. It shows some of the parts here that we have. The stator, this is the part of the motor that stays still, it's stator. We have the armature or rotor. This is the part that rotates. We have some permanent magnets here that are going to interact with the electromagnetic field that we create with a DC current through here, through this rotor. And this is that part that I was talking about that changes the direction of that magnetic field. Now we have a DC power source that's flowing this way around the circuit always. And so if we always had it flowing in that direction through the armature, the field would always be in the same direction. And as soon as this north pole got to the north pole, it would stop spinning. So the commutator's job is to switch these connections from one side to the other so that the field constantly flips in this rotor as it goes around in a circle. Now, most industrial DC motors, and in fact most of the DC motors that you have in your kitchen, things like that, they're using, instead of permanent magnets in the stator, they'll use field windings that are creating a magnetic field to interact with the magnetic field that's created in the rotor. And so this field winding can be done in a couple of different ways, and that it affects the way that the DC motor works. So we're going to talk about that in a few minutes here. And another thing to note is that the armature of the DC motor, in spinning, it has that momentum and energy to generate its own voltage. The voltage that it generates is counter to the voltage that's coming into the motor. And so we call that the counter electromotive force, that the momentum of the armature is resisting the energy that's coming into the motor. That resistance actually resists the flow of current into the motor. So when the motor is spinning at top speed, it actually draws the least amount of current. When the motor is completely stopped, that's when it's really going to draw the most amount of current it can draw until the motor gets up to speed. With a DC motor, as you load it and slow it down, it'll draw more current to try and speed up and generate more torque to match that load that's being drawn on it. So as you can see from this diagram, as the load increases, the current running into that rotor increases because the counter electromotive force that's resisting that current is going down because the speed is going down. And that causes the torque to go up because we're getting more current in there. Now, as the load decreases, the rotor current decreases, the torque decreases, the speed goes up, and the counter electromotive force goes up. So when you try to load a DC motor down, when you try to stop that thing from spinning, it's automatically going to try and draw more current to maintain its speed and produce more torque to try and get back up to what it wants to naturally run at.